the chat. All right, I see the YouTube live stream up. That's good. All right. Anyone can give me their own explanation of what CAD is and how you can use it. Yep, so computer-aided design is the use of computers to aid in creation, modification, analysis, and optimization of a design. Why do we need this math for CAD? Well, math is the basis of your CAD, because without math, you don't have something to look at, something to see, or the object in CAD. Because if you ask veterans in mechanical and engineering and the veterans in the CAD industry, they will tell you the first CAD is drawings. The first CAD is the simplest of 2D drawings. And there's a reason for that. As you can see over here on the, there's a kind of a drawing kind of indicating very basic mechanical components. These can be very complex, very basic, but they kind of indicate the scale of the product and so forth. All these 2D drawings will make up a 3D design at a certain point. And engineers will kind of lay them out and draw them out, kind of create that. As you can see in the bottom right corner, right? This is a photo from, I believe, the 1950s and 1970s. These rooms were filled with engineers. And you see those stencils, you see miles of paper, graph paper, and just the rulers, all sorts of things. They had to calculate everything by hand. I remember one of my instructors told me about the time he took 3 days to calculate the curvature of a door handle. 3 days, and like an entire notebook full of paper. There is so much math that goes into CAD, and I will be using that as kind of a demonstration and a visualization for how you can use it as well. All right, so like applications in professional settings as well. Some things like in programming, right? A lot of you guys are very interested in programming. Programming is a huge part of the future as we move on to more technology innovative age. And that includes things like video game development, software, front end. And you have all these different applications that span all over computer science. Something that a lot of people have said, and well, this is sort of true to some extent. People say programming is mostly logic and might not include as much math. Well, that is true to some extent. Programming does use a heavy amount of math in it in certain applications, and that enables you to kind of choose and pick which profession you want. And of course, the more specialized you are, the more, I guess, like you're going to get paid for it, because you're more knowledgeable about this part of it as well. But there's so much hidden math in all of these things that understanding how it works, that would definitely help your workflow, help you do your job in this aspect. So like things like video game development, your physics in game, you have your 3D games or your 2D games. All those things have bits and pieces of math connected to them. You have items, you have servers, you have all these different things that all come together. You also want code optimization. Something that people overlook is code needs to be optimized for your system to run very well. If you've ever loaded up a game and if the graphics are okay-ish and it just tanks your computer, you're seeing very low frame rates, it's not running very well, your GPU is on fire, it's not a very good, fun game to play. You won't have many people buying your game. So programmers will try to optimize this to the best of their abilities using the computers that we have, because computers are limited as is. They have limited memory, limited processing power. We want to utilize that the best we can for what the applications that we have. All right, and then some misuses is like 3D modeling, artwork, photography. So there's a surprising amount of math involved in the more creative aspects of your jobs and of different people's lives. And that is definitely, I'll definitely explain some uses of that the presentation for today. This is an additional slide for why we need math for programming. So I'm pretty sure you guys have heard the buzzword artificial intelligence. Artificial intelligence is used everywhere, and there's good reason for it. Artificial intelligence is one of the things that we use to optimize our softwares, our programs, and kind of make our lives easier. Stuff that would take hours and hours, and just honestly very, very painstaking work for a normal person can be done in seconds by AI. And that requires vast amounts of data, vast amounts of processing power, vast amounts of different things that you need to process. Well, yeah, process again. And this needs equations. All this stuff is generated by algorithms and programs. And who creates those algorithms and programs? The programmer. And the programmer needs to have this understanding of math to kind of create these things. Like reasons why it's so powerful. Have you seen, why does YouTube feel so addicting? Why does social media like draw so much of our time every single day? Why does Amazon know what I want to buy? And different things like this. As you can see in these pictures over here, one of the examples I gave was a Fastpass or like a amusement park. So I'm going to kind of give the example of an amusement park. So let's bring up my notepad. I'm going to be using this a lot during the presentation to kind of give you visual representation. Say I have amusement park. I don't know why the handwriting is a bit off there. Amusement park. And I don't, yep, the spelling is off as well, but bear with me here. I have a bunch of roller coasters, something like that. I have rides, carnivals. I have all these things packaged within a brand new park. And it opens, opening ceremony, everything happens. But you get, say, 9,000 guests on the first day. And they all like are going around the park. There's so many different people. How do I make sure that I get the most money and the guests get the most enjoyment out of that? And that is one of the questions that Disney has, and also other amusement parks have thought about as they've kind of evolved. One incredible use of this technology and use of math to kind of solve this problem is by the Fastpass system. The Fastpass, I don't know if you guys know about this or have gone to an amusement park that has one, but Fastpass is kind of a thing that you can pay for that can allow you to jump in line. While it sounds simple at first, there's actually a lot that goes behind it, including something that schedules the time frame for you to use the Fastpass, different other things like that. There's also things like the app that apps that the amusement parks have. Like I went to Cedar Point 2 weeks ago. One of the things that we used was this app that showed the waiting times for each ride and which ride was the closest. And it would kind of give us these numbers. And these numbers aren't there just by random. They're calculated and they're there for a reason. And especially if you have like a ride that's extremely popular. Like I have a ride that's like biggest coaster in the world. Like I have my dragster that goes from all this height and all the way down. It's very, very popular. Line is 2 hours long. It's going to be very, very hard for a lot of people to enjoy it if their entire day is stuck in that line. So you have things like, you have the app. It gives you different options. You have I don't know how to spell that ride's name, but it's another ride. You can give people a wait time of say 20 minutes. 20 minutes. Even if the ride, even if the waiting isn't exactly 20 minutes, that will attract people away from say your most popular ride and kind of spread out the population of your park. So I have my park over here. If they're all trying to pile in on one ride over here, like they're all over, they're all trying to populate this one area of the park. They're all cramped in here. They're not going to go around the park. They're not going to spend money. But if I make sure the app separates them into different places, and part of this is they use a Fastpass system, then they can get a more and more better experience from the park. There's a very interesting video on the Fastpass system that I'm going to post in the chat so you guys can look at it here. This is a video kind of explaining how it works and how it was developed and the kind of genius behind it. But you can give that a watch if you guys like, but it's just there. I'm going to move on from programming. Just because there's so much involvement there. I'm just going to go into MISC applications as well. So you're looking at this and like, music, art, what does it have to do with math? And you'd be right in some aspect. Music and art is a different aspect that you wouldn't really see too often intersecting with math, except it does, and it does a lot. The most common example that I like to give is music. What makes something like a violin? The violin's way too far away. What makes something like a violin? A violin. You have your standard strings over here. What makes it make sound? Can anyone give me an example? Tell me why something like a violin or a piano makes sound. Any music enthusiasts in the chat that can tell me that? Vibration. And what do those vibrations generate? Does anyone know what it looks like on a very, very small scale? Waves. And waves, I assure you, have a lot to do with math. And I'm going to kind of drag in one of these, kind of give a visual representation. But the reason we hear sound at all is because like this motion creates a vibration of the air. And this is the sound that we hear, as you can see over here in this photo. And this is a very, this contains a lot of different elements. You can see over here, like the amplitude, the wavelength, the cycle, and like the time for a cycle. All these different things make up a wave. And there's so much behind that as well. You also get things that are not music related, like in 3D sculpting, like the patterns you use, materials and meshes generate in all of these different things to create the end product. What you'll see a lot of it recently is these very weird, like generated artwork by AI or by different programs. And it just creates like this very like surreal kind of artwork piece. And all these different things will use math in some form. Now over here, you can see the ratio of guitar. Like if you get further and further away from the area that you pluck, you'll experience a different note. And there's a science behind this, as you can see over here by the fractions involved. There's so much behind this. Again, I'm not here to teach you like the specifics of the equation, specifics of that thing. I'm here to kind of show you the applications and what the concepts can do. All right, so let's get into questions really quick. I know you guys have been probably been saving that for a while. And I have some applications I've saved up on my computer, mostly with like Fusion 360, Python, and Scratch, if you guys are interested in that. So again, I'll open that up to participant questions, so we can get started with that. I'm going to remind everyone of the format that we're following for over here. So it's like name, grade, question about math concept, and why are you confused about it? Like, what part of it are you confused about? I'm going to open up to that. Anyone have a question so far? While people think of their questions, I'm gonna go to my first example of a concept. Let's see. I have a few projects over here, so I'm gonna probably start off something simple. See. So this is my first example. This is a skateboard wheel I made for my electric skateboard. So for those of you who don't know what an electric skateboard is something very dangerous that you should probably not get into because it is very fast and it's a skateboard with a battery strapped on it and a bunch of motors. It goes very fast. But I've taken a fascination with them because I can create different parts, and all these different parts can help kind of modify this board into something that suits more of the application I like. So one of the different things I applied to it is an idea for a wheel. So this wheel, like since the normal wheels are just like circular, I'm gonna search up longboard wheels to kind of give a. The normal longboard wheels are flat along the top, and there's a good reason for that. Along flat, very like good pavement, you have more contact patch. I'm gonna demonstrate over here. Actually, let me see if I can get my other computer up because it has better drawing capabilities. See if I can stop share over here and change it over to this one. All right, I see my other thing. I'm going to share the screen of this one. For some reason, it's not showing my, oh, there it is. There we go. Hopefully you guys can see that right now. All right, there it is. I've got my trusty pen in front of me. Make sure this looks as good as possible. So back to my example. So I'm trying to create a wheel, right? The normal longboard wheels, they're great, but they have one flaw. They're very flat and flat for a reason. So if I have a cylinder shape like this, and I have this as a contact patch, is what's called a contact patch. This is going to be the part that's touching the pavement, this flat pavement over here. And this stuff is made out of very, very rubbery, very stiff, well, not stiff, but like it will grip onto the ground. So it's very grippy material. But basically, this is my flat contact patch. You guys have probably learned about surface area through cylinders or stuff like that, but you can kind of see that over here. And basically, if I peeled off, like think of this as an aluminum can, and this is like the wrapping of the aluminum can. But if I peeled it off like this, I have this large rectangle like this. And this is the point that's touching the ground over here. And this is good if you're on very, very flat ground and this very, very smooth ground, because all of a sudden, if I have a bump, I have cracks, I have all these different things over here. What that will do is all of a sudden, my contact patch goes from this to this because of that pebble. So I want to change that. I want to make it so that there's more grip. And it works better in off-road environments where this is not a flat road. This is grass. This is muddy trail. This is dirt. I want to make it work in that scenario. So what I'm going to do is I'm going to create a new wheel. This new wheel is going to be very similar to an off-road tire that you normally see. I am also very good at great at drawing circles. There we go. Yep. So this new wheel is going to have a few things that don't include my bad drawing skills. It isn't going to include a more circular design that you see in tires. That is a terrible wheel design, but bear with me for a moment. So the contact patch all of a sudden becomes this thing. It's a bit sleeker. It's not as good on flat roads. But it has these side areas over here that act as additional contact path. And what can I do to make it even better in terms of grip? Anyone can give a clue in chat? What are those patterns that we see on tires? Making the surface more rough. That is exactly it. Because, sorry, the back of my throat is going right now. So if you look at tires, right, you won't see it flat. You will rarely ever see a very flat tire. And if you do see a very flat tire, you should stay away from that car. But like, there's a reason for that. If you look in the bottom of a tire, it's usually treaded, what's called treaded. I cannot draw treading, but I'll try. Something like that. And it's part of the pattern over here. It can go in multiple ways, but if you're like, what is the point of that? Shouldn't my goal be to make it more contact? Yes, it is more contact in another way. The idea behind adhesion and surface area and contact area, let me check that. There, that's good. Is that you want more of your material and more like surface area touching your ground or your other object. Because if we look at something like tape, right? Tape, a strip of tape. Does anyone know what makes tape sticky? Anyone know what makes tape sticky? Or what makes things sticky in general? All right, I'll kind of answer that. So if we zoom in on a molecular form of tape, you'll see that it is not flat. It's not something that's like glass, very uniform like that. It is something that is more rough. It is like very, very rough. There's like all this stuff going up. It has all this contact area. And the same thing with rubber. If you zoom in very, very far on rubber, it is very rough in the surface. And what that allows it to do is when you apply force on that surface, right? All that roughness, like apply force on it, it will like have more contact. It will have more friction between those two. It will require more force to push it across. So that is our friction force. And that is why those things stick. And that is a goal we have over here. Okay, enough about that. Let's talk about a few concepts in math. So the first one we're going to do is circular. Oh, I think my thing's lagging. I think my one note just crashed. Hold on. Yep, it crashed. Sorry about that. I wish technology worked on time like it does normally, but all right, there we go. Back to sharing screen. Hopefully it doesn't crash again. All right, there is our window again. I'm going to go past the other demonstrations, but we are going to do a few things. Circular geometry. And patterns. And multiplication. You guys know multiplication, but in case you guys are a bit young over there, kind of reinforce that a bit more. Surface area, SA, plus volume, plus another thing. I'm going to do some calculus as well. Calculus, cross-sectional area. Cross-sectional area, circular geometry, patterns. Did I put 3 T's on patterns? You never saw that. Multiplication, all these different things. Surface area, volume. There's so much math involved in this one design, and yet I use very little of it, but it's very essential for understanding how I designed it. So I'm going to go back to my Fusion 360 design right over here and kind of go back to my own process when I was developing this. So luckily with Fusion 360, you guys can see the process and the steps I took to create this design. Like if I play this out right now, hopefully you guys can see the progress that it makes. Actually, it doesn't because it didn't play. I don't understand why it's getting stuck. Oh, I need to go back to the beginning first. Okay, there we go. So as you can see, I start over here with a sketch and I make it a circle, and then I added a tread on it and all these different things. And as you can see over there, it just gets more and more complicated as I add on more and more things. But I'll kind of add a different math concept to each different part of here. So let's go back to the beginning. I start off with the most basic sketch in the world. It is a circle. I give it a dimension with these things. This is like a variable that I can put in a number to represent. And that is our first concept, or one of our first concepts for this. Let's go back over here. So multiplication, I'm going to add a variable, okay, if I can draw variables. Variables. Your X, Y, and Z. Y, and Z. But there can be infinite amount of variables depending on what letter representation you get them. Let's go back over here and go to, I think they moved it actually. Nope, there's change parameters. Model parameters over here. The great thing is I can change the part of the sketch over here. So I'm going to go to sketch 1 and go to the, you'll see the exact value of this thing, these things. And what we can get is we can get an expression, and we can get an exact value for that expression. And this can interlock with other things. Say if I wanted this value over here, the overall like inner diameter of this to be half the size of my largest diameter, my largest circle over here. So I can put in 105 divided by E, or E2 divided by 2. I can make that half of it. And all of a sudden you see that change right over there. I'm going to change that back, but that is example of variables over there. All right, let's go on. So in terms of circles, right, we have a few things here. We have our circular pattern over here. Our circular pattern is a tool that we use to make more circles around a center, around the axis. So over here, I can select the center point, this being the origin over here, and it just kind of creates more and more around them. But I'm going to get back to my notebook. Where is the thing? There we go. Sorry, this pen is being rebellious. Oh, I'm using the wrong pen. Sorry about that. So I have a circle, right? And if I divide it into parts, we get different things in degrees. We get degrees. And if they're all equal degrees, we can then determine the angle that they're at. And this is very important because one of the things that I did early on in our classes, especially when creating circular patterns, is creating fidget spinners. Fidget spinners, the thing that was a trend like 5 years ago and is no longer a trend. But creating fidget spinners in Cad is very important because it teaches us a few things. First, it teaches us angles, like the angle from here, the angle of here, the angle of here. If I have 3 sides, what is the angle between my sides? Can anyone answer that for me? 120 degrees, exactly. So you have 120 degrees between each of those sides. And that is very important. But you can also use that in a lot of different ways. Mainly for estimating the what length this needs to be, or like the length between these objects. Because believe it or not, if I draw a center from this circle, a center to this circle, and a center to this circle, there's a distance, and it creates even more triangles from that. And based on that triangle, I can determine things like the distance from these two things. I can determine the angle of this, and I can determine things like the distance from these two circles or other things as well. Kind of show you applications of that in a second, but it is very important as well. Here, we get back over here. So does anyone know, I have 5 circles over here and is rotated around a circle. Can anyone tell me what the what angle it is from each individual circle? What is the angle of between each circle in this picture? 72 degrees. I believe that's the correct answer. So if we take 360 divided by 5, and we have 72. And if we take over here, and over here, and over here, we have exactly 72 degrees. That's another feature of Fusion 360. Our measure tool kind of gives us a bit of insight into that. So once we finish the sketch, we can kind of extrude it and then take out that and keep on using more and more of that same thing. And we eventually make it to our trim using emboss, which uses the same concept as well. Now onto a little bit of, let's say, calculus right now. In calculus 2, we have this thing that revolves around the axis. We have a line, and then we have an object. We have an equation usually. And this equation can be like a solid line that goes upwards like this. And it caps out a certain distance, say like a limit of 1. And we have this shape over here. This is not a perfect right triangle, but it is a, if I can make it here. That's right. I can deal with that later, but premise is I have a shape over here. This is either area under a graph, but if I rotate it around an object, say over here, revolve around this object over here, you'll see that I can create an entire shape out of it. This is what we have in calculus 2. Revolution. We have things like surface area we can derive from it. We have things like volume, because if we determine the the shape's area at a certain point, we can determine the entire volume, entire thing, because calculus, as you guys probably know, is thin slices or thin parts added up over time. I'll kind of, if you guys want, I can give a further explanation, but there's a lot of different theory and a lot of different practice involved in that. Discs, washers, stuff like that. All these things help a lot. And that's one part of the revolve and the tire over here, because then we get to this thing over here where I use revolve to, actually I lied. I don't think there's a revolve in this program. But we have things like chamfers. Chamfers are essentially, we take a corner of a sharp edge and then we kind of chamfer it out. And this program, the main thing drawback about CAD is versus what we had in the past. The thing that I showed you with a room full of engineers drawing stuff out. CAD does the math automatically for you, so we don't get to see the very detailed stuff that's behind it. Because if we look at a fillet, which is essentially a smoothing of the surface, we have a tangent, which is part of a math concept that you'll learn. And this tangent is given a value, a radius, and that is applied to change the curvature of a shape over here. And that's one thing that you can use a tangent for. So hopefully, if you once you guys learn tangent, you'll be like, oh, that I can use that in Fusion 360. As we go around, it gets more and more complex, adding more and more features. So I'm going to jump back to this since I'm getting kind of distracted with the one wheel design. But let's move on to something else if no one has any other questions about specific stuff. Anyone have any questions about specific math concepts and how they relate? Because if not, I'll be going into our battery demonstration and our physics and our Python and our other things as well, or Scratch as well. All right, doesn't seem to be any questions. So let's move into our battery design. Sorry, my throat is still very congested. Just allergy season. All right, so battery designs. So you might know batteries from the from things like Tesla cars. Tesla cars is like this huge thing that people want nowadays because it's a clean electric car. It has so many batteries in it that power it to go hundreds and hundreds of miles. And it's all stored under a car hood. And it's a pretty novel idea. And we have Tesla battery. And wow, we have these dozens and dozens of these individually wrapped lithium cells that appear in circular designs. These are called cylindrical cells. And they're the most popular kind of cell that people have at the moment. These make up a lot of your electric vehicles, your electric bikes, your electric scooters, your, of course, my electric skateboards. And fortunately, while at my internship last year, I had the opportunity to design a lot of these packs. And I designed battery packs for electric motorcycles. I designed batteries for different applications that ranges from submarines to other things. So these batteries are circular in shape, which provides a lot of great design choices we have for them. And as you guys can see over here, they're very densely packed. So you guys have to get this design right, especially if it's an electric car. So let's design a battery pack. And let's do that in our example over here. I'm going to delete the stuff that we've drawn so far. All right, there we go. Let's create a sketch. So this is Fusion 360 again. Everything starts from a sketch. So if I would say starting off with a battery pack, right? I'm going to give it, our cell is, so it's 18650. So the dimension's 18 millimeters. In diameter for a cell. Actually, let me see if I can draw this out, make it a bit easier. 18 millimeters in diameter. 18 millimeters. And I want to pack as many of these in a battery pack as possible in the shortest amount of space. These battery packs in cars are enormous. They take up the entire belly of the car. They're insanely large and heavy. And we want to reduce as much of that as possible. So we have each of these individual cells. They are circles of if your first thought is to build a pack like a rectangle, right? Rectangle like this. And I have cells that go up, 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 and like and keep on going up like that. Let's design that in Fusion 360. So I create a rectangular pattern. I create using the objects and directions. And I can go in two directions. So I want, that's not a realistic size, but just say like, if you guys don't know the relation between, there's a lot of different concepts I need to explain. So sorry if I skip anything, or please speak up if you aren't sure about anything I said, but in batteries, this is a very quick explanation. There's the cell voltage. It's like electric potential of a cell. And we have our capacity, how much it can discharge per hour. And usually for a cell like this, it's nominal 3.6, 4.2 max voltage. So we have these as our numbers for volts. And our capacity usually ranges from like 1,000 to like 3,000 or even 5,000 nowadays, milliamp hours, which is really just 1 to 3 amp hours, since milli is 1,000. All right, so we have these numbers, and if we connect things in series, like from, let's say this is a battery, right? We have plus, minus, plus, minus, like that. This is series. What this does is I take a 4.2 volt, and a 4.2 volt, 4.2 volt, 4.2 volt. And I have them all in a line that connects to a light bulb. This is a very shoddily drawn light bulb, but it is a light bulb. So the current going through, or the voltage going through that, is suddenly doubled, because I'm now adding these two voltages together, and it's 8.4 volts now total for that light bulb. But if I connect them in parallel, I then change the capacity of the cell. So I have capacity, this is in parallel. So I have these packs of parallel cells. These are all positive, 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 negative, 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 like that. And they're all connected. And then my output over here is going to be the same voltage. Same voltage, 4.2 volts. But our capacity is going to be adding on the capacity of each. So the capacity is going to be 5x, or 5 times capacity. So you need to combine these different things when using, when making a battery. All right, back from that tangent, let's go back to designing a battery. let's have it like that, right? So our standard pack voltage is probably 48 volts. That's a pretty standard set for our voltage. And we're going to have our pack go like series go left or go right, and then our parallel go up. Let's give it 12. 12 times 3 is 48 volts, like that. And up we have 3, so 3 times the capacity. And I was like, okay. And all of a sudden, I have all these different cells laid out in front of me. I could make a pack here and there. It would be really simple. All I need to do is just rope in a rectangle over it, and I have a pack. I have a pack that I can put cells in. I just weld them together and I have a pack. But I don't want to do that. If we look at the cells in the picture from the Tesla photo, you'll notice something. They're not in rectangular forms. They're in this zigzag, or in this case, so they can fit closer together. So they have higher energy density. So you don't need more space. More space is more problems. So how do we do that? So again, I'm going to tackle a few things that we mentioned. Our circular geometry, our patterns, and I'm going to add on geometry. Oh, that is very much tree using SOHCAHTOA. You guys remember what SOHCAHTOA is? For a lot of you guys, younger guys, or younger people in chat, this might not be as recognizable, but for those in a higher math, this is instantly recognizable. Sine, cosine, tangent. Sine, oh, there. Sine, oh, sine, cosine, tangent. Sine, cosine, tangent. How can we use this to make our pack more useful? So how can we create it more densely? So let's do it. 18. I'm going to create a triangle. And in this case, it's going to be a, let's say, 20-ish, 22. Like that, right? I have it packed pretty well in between. And if I create an equilateral triangle, you guys remember what equilateral triangle is, right? Equilateral triangle is something that has all sides same length. Do that over here. So here, equal. And we have our equilateral triangle. And if I add another one, just 18 millimeters over here, we have exact kind of combination that minimizes the amount of space between all these. So I can change this 20 and they all become closer. I can change this to 40 and they all become further apart. It depends on this. So depending on this, I can create a program to do that. And that's exactly what I did. I'm kind of skipping a few steps here, but this is a Python program I wrote. It is pretty long. It is also kind of disorganized, but ignore that part for now. It has 3 components to it. Or actually, it has a bit more than 3, but 3 major components. It asks for how many cells is in a series, which basically asks for what voltage is your end goal. It has how many cells are in parallel. What is your capacity that you have in goal? And it has your angle of your cells. What angle do you want your cells to be at? And this is the angle we have over here. And as you can see over here, if I take a look at the angle between these, it's 60 degrees. So that is another thing that I can enter. So if I run this program, there it is. I can enter in these different integers from our Python program over here. So Python program, I can assign different variables like cell series, cell parallel, angle, different other things. And it takes the coordinates of that. And every time I give it some coordinates, it will take that program and it will do it to drop a circle wherever I need it. So let's take that in practice. So let's go over here. Over here, let me take a look. Over here, so how many series cells are in series? I'm going to give it 12. That way there's 48 volts in a pack, which is pretty standard for something for your normal electric bike, electric skateboard, electric scooter. How many cells are in parallel? So this is the capacity of the cells, so let's give it 3. And what angle do you want your cells to be at? I'm going to give it an angle of 60 like we did before. And how many millimeters of spacing do you want between each cell? This is important as well because like over here, the closer the cells are, say this is 18. There we go. These are literally on top of each other. There's no area for the like casing to kind of hold them together. So what I need to do is I need to make it, there it is. I need to make it 19. So if the distance from here to here is 19, the distance from the circle to circle is 1 millimeter. That kind of times to the math over here. So let's make it 1 millimeter spacing. And what cell type? I've already pre-programmed each cell type. These are the 3 most common cell types I've used. So 18650, 26650, and 21700 cells. These all vary in diameter, width, length, and usage, but they're all standard and different sizes. So I'm going to give it to a 3, a 21700, which is the one I use in my electric skateboard. They're pretty large. What is the individual cell capacity? I'm going to give it 3 amp hours. Polarity caps, yes, I'm going to give it polarity caps because cells have a positive and a negative sign, and I want to model that. So yes. Would you like to name the file? I'm going to give it test2. Yes. And I calculate over here. Your cell is a nominal voltage of 3.6, diameter of 21. So final completed array will have a voltage of 32 volts and a wattage of 388 watts. So let's take a look at that file really quick. I'm going to open up my Autodesk viewer. This is a pretest. Don't worry. This is something that was previously done. Upload new file. There we go. And now you can see that each of these cells are spaced alongside this diagram and have the polarity. So like you have your positive and negative sides attached. And of course it is at a 60-degree angle. I think I did at the wrong 60-degree angle. So that's why it looks a bit weird. But basically what I used in here is, as you can see over here, when I was creating this, let me find the while loop. Yep, so I used a while loop, a for loop over here. For the how many in series, I use math concepts like distance between the cells. I added that with the angle distance. And the angle distance was something I calculated using geometry, using the sine, cosine, tangent. Because one of the things that you'll learn about in school, especially when it comes to triangles, we have our triangles over here. We have circles for the cells. We have a triangle in between. And if we know the angle that we have, say this is 30 degrees. Well, it's not 30 degrees, it's 60 degrees, 60 degrees. And I have a length of say 19 millimeters between each cell. How far up is this line right over here? Can anyone answer that for me real quick? So I have this line over here. I have 60 degrees of angle over here. And this bottom line over here is 19 millimeters, or actually scratch that. This is, I'm going to make that 20 millimeters. 20 millimeters from here to here. Can anyone tell me how long this, how far up this this top point is? As if we remember, so COA, sine, cosine, tangent. Can anyone solve me that for me really quick? You might need a calculator, but that's fine. Yep, no problem. I'll solve it over here. So we have our first value, which is our angle. And we're trying to find the opposite value, which is O over H. So we have our value we're trying to find, which is our Y value, Y over the thing that we know. Hypotenuse. And this, of course, is our 20 millimeters. 20 millimeters. And that is equal to our sine 30 or sine 60. And that is how we solve for our y in this direction. So if we look back over here, over Fusion 360, that is exactly what we need to kind of complete the triangle over here. And create the cells in the array. Over here. All right, any other questions about this particular design? I'm going to move on to video game application, Scratch, physics, and acceleration after this, and also some calculus concepts along with it in a second. Any specific questions about projects you've worked on in the past? Say like you're part of a robotics team and you recently finished up something really cool. Is there something that you project that you have done that you want like some kind of math explanation for, or something that you can involve math in? All right, so it doesn't look like it. Let's move on into our other and probably final application before we end today. Let's go to Scratch. So Scratch is one of the softwares that you've probably learned very early on, either in elementary school or somewhere else. But something that you'll notice is that when you have when you're programming in Scratch, either if you're trying to make a platformer or something like that, right? That like, let me try to kind of draw that out really quick. So I have a sprite. I have basic code, like if left arrow, I move 10 units to the left. If a left arrow and so forth for right arrow, and up and down. This works good if if you have a maze puzzle, if you have something like a maze that you need to navigate through. And you're trying to get them through that. But if you want to simulate something like Super Mario, right? I'm pretty sure some of you guys have played Super Mario before, right? So you have your sprite, your Italian plumber in this case. I cannot draw a cap for some reason, but you have your Italian plumber and he's trying to jump up. He's jumping up to stomp a Goomba, right? Like that. And you need him to jump up, but when you program him to jump up, right, he needs to come back down to gravity. You have forces of gravity and you have your forces pushing upwards. So you have your up and your down. But the thing that a lot of people do when they program it is they'll have it like, oh, I'll go up go up for 5 seconds. That is way too long. I'm going to say 2 seconds. Go up for 2 seconds. So what ends up happening is the sprite goes up and then slowly comes down. It's like tossing a feather up and tossing watching it fall down. Watching the feather fall down. It is not fluid. It's not what you expect from falling. Falling requires you to accelerate. You have all these variables involved, acceleration, which means you speed up as you go along. So I'm going to kind of get into a bit of physics with it, or physics and calculus. So say if physics, calculus, and a bit of algebra. I promise you all these things make sense later down the line as you guys look. So you guys have seen your quadratic formulas, right? Quadratic formulas. You guys remember? Can you guys give the quadratic formula in chat? I just want to see if you guys remember. Anyone remember the quadratic formula? Yep, so I see the 2 quadratic formulas over there, and that's really good. So one of the things that we need with the quadratic formula is that we have acceleration, and especially it comes from the x squared. So in this case, our x squared is downwards, so it's going downwards. And we have our c plus c, which is our x-intercept over there. So if I was on top of this castle and I need to jump onto this Goomba all the way down there, I need to, our C would be our starting point. This is our intercept point. But that's not important because we're focusing on our acceleration. Because if we plot our x squared, we have a acceleration graph. Like it starts out kind of slowly, right? It starts out slowly, but as it goes up and up and up, it keeps on increasing in height. It keeps on doing that. Later down the line, you'll learn in calculus. And this is a very short rundown, but calculus is very simple when you understand that it is measuring the distance of or distance over change. And that kind of reflects in your equation over here. But our, I think the acceleration of gravity is 9.8 meters a second, something like that. But that means the longer we fall, the faster we go, and faster it gets. It gets very fast. So how can we program this in? So in Scratch over here, you guys can see over here that I change a few things. One, I added a variable. So this, again, it's a variable. It's involved in a lot of math that we do. If you guys haven't gone to Algebra 1 yet, but variables represent a certain number and can change depending on how they're altered. And over here, we just happen to have our variable set to xv and yv. Can anyone give me a guess on what those two mean? I'm just going to fill in the blank really quick. So that is x velocity and y velocity. Because think about it really quick. If I have a position versus time graph over here, this is x, this is y. And I have a linear kind of a position over here, and it keeps on going up. My velocity, or the rate of change between the two positions, is going to remain the same. So velocity set to a certain number. And if I increase that number, the velocity is going to increase and increase and increase and go up and up and up. And I can change that. So depending on the key that I input, right? So my left or right, instead of changing the direction or the how many units it moves, I'm going to change the velocity or how fast it moves. So instead of having the linear up at the same speed and down at the same speed, I have up like very fast up, and then it slows down as it goes up. On the way down, it starts out slow, and then speeds up as you get closer and closer to the ground. It's just gaining velocity. So we need to program that in acceleration as well. And you guys can see that over here by my change X by this certain amount, change Y by a certain amount. And you can see over here, I change it. It's very intricate part of the math. You can see over here, change Y by that, and the end product shows for itself. Because if I move it and jump up, you'll see that it moves very naturally instead of just moving up and then slowly coming back down. You can see the X and Y values change over here. Take a screenshot of that so you can see that. So X and Y. If you guys want, I can give you a bit more explanation on calculus and how that intertwines with derivatives. Even if you're in a lower math and don't quite know what a derivative is, let me find one. Forgot the name of the channel. Something like that. But basically, I would recommend looking into a video explaining on the logic of calculus, the logic of your graphs and the different things that it has. All right, we have around 5 minutes left of this seminar. So again, if you guys want to ask anything specific, you guys can ask it. Oh, over here. Yeah, I forgot to also run the physics problem that I had where I launch a ball and you can see the position versus time and also the different position velocity. And over here, the program also uses something to the program uses a physics thing to add drag using a parachute. So say if you're launching something by NASA and you want it to fall in an exact spot and know the position of it, you can calculate the rough position using like drag or using a position like this. All right, guys. Again, if you guys have any questions, we have 5 minutes left. Ask them while you can. Yep, Aiden, go ahead. Oh, no problem. Anyone else have this have something they really like about math that they've seen in real life and they've used before in real life that they want to share with us? Nope, not yet. All right, so I'm going to move on to our last slide, which is basically a reflection. Is there anything that I missed today that you want me to cover? Like any very basic, even very basic math concepts you guys want me to cover? It's not. So kind of just summarizing the things that we've done today. I hope you guys have kind of like gotten the idea of why math is very important, because you have a lot of very interesting things you can apply math to, and all the things that you do. Like a lot of the projects I've been working on, I don't even realize I'm doing math by the time I start working on them, especially in robotics and like the things I 3D print. So much stuff that goes on, and kind of trying to understand that before you learn that stuff makes it so much easier to learn, especially once you get to calculus. So again, it's very, very important. And again, like I am a teacher at NYE, so like if you guys have any other questions, feel free to ask me or reach out. I do teach 2 classes this summer and classes in the fall, so look out for those if you guys can. I do teach a class on Fusion 360 and another on Tinkercad. So if you're looking forward to more content similar to this, definitely try to sign up if you can. Other than that, we have around 1 or 2 minutes left. I'm going to end it when it gets to 9, but you guys are free to kind of stick on and ask me any questions if you want. All right, guys, you guys have been a really great audience. Thank you guys so much for attending. It means so much to me. Again, like if there's something that I could have done better, or if there's something that I didn't cover, feel free to ask or reach out to me in the future. All right, guys, thank you guys so much again. I will hopefully see you in a future class or at NYU event. All right, thank you guys.